All right, so let's talk about electric field lines or electric fields. We have learned that we have electrical charges or electrically charged objects, and they have the ability to interact with other electric charges. We've learned from Coulomb's law that the magnitude of those electric charges and the distance between them will affect the force that they experience. That force can either be an attractive force so that they are drawn towards each other, or a repulsive force so that they are pushed or move away from each other. Electric field is a term that refers to the space or the area surrounding our electrically charged object or particle. You can see from these illustrations that we have vectors that we are using to represent this electric field, and we often call these electric field lines. They are arrows with a very specific direction or pattern to their direction. It says here that it surrounds any charged object, so make sure that you understand that the electric field is going to surround my electric charge. So you see that those lines are located all the way around our positive and our negatively charged things. The closer we get to the electric charge, the stronger the electric field is. If we look at our illustrations, we can see that the way that these vectors are drawn, and because it's shown basically as a perimeter, or we have a circular shape here to our electric charge that we can illustrate that it's going in all directions all the way around 360 degrees, we can see that these field lines are going to be more crowded as we get closer to our positive or negative charge, and they're going to have more space between them as we look farther away from those charges. So when we draw our electric field lines, we can see from the illustration that there is a greater concentration of lines closer to the source, which means that we have a stronger electric field closest to the source. You can see that some of these electric charges are interacting so that there is what we could maybe describe as a connection between the two, and some of them are interacting so that there is a lack of connection, or maybe we want to say that they almost seem to be bending away in order to avoid each other. So we should already know that like charges are going to repel, meaning two negatives are going to want to move away or push away from each other. Two positives are going to want to separate. If we have a positive and a negative, we say opposites attract, and so they will be drawn towards each other. As a general rule, our electric field lines have a direction. If you will notice in the previous illustrations and then in the images that we see here, there is definitely a direction for our field lines. All of the positively charged particles had the vectors drawn so that the arrows were pointing away from them. All of the negatively charged particles had the vectors drawn so that they were pointing towards. So we say that the electric field lines are going to point out or away from the positive and into or towards the negative. Now, it says here on the slide that they are going to point in the direction that a positive test charge would move. So if it's easier to remember that we are illustrating what a positive charge particle would experience, then it's, I think, a little bit more straightforward, and so we can then understand that my direction is specific, because if I were to take some positively charged particle and place it here, because these are both positives, like charges repel, and so this object is going to be pushed away. So we show our electric field lines to point away from that positive charge, because that's what this small little positive would experience. If I were to bring a positively charged thing and place it right here, because my source charge is a negative, then this little charge would be attracted towards that negative charge. So we're going to draw our electric field lines around our negatively charged objects or particles as being in or towards it, because that's what this little charge would indeed experience. So that's how you're supposed to know what direction those arrows or our field lines should be pointed. It shows you over here on the far left-hand side, if you have both a positive and a negative, make sure that you illustrate that there is an interaction by showing those field lines to go all the way across. Notice that the direction here is from the positive to the negative, so it's pointing in the direction of the negatively charged object. If we were to look with our focus on the positively charged side of our illustration, we can see that indeed those field lines are pointing away from the positive. So as I stated before, we could see from some illustrations that there seemed to be an interaction, and in some illustrations it seemed like those charges were avoiding each other, and that's exactly what is happening. When we have two charged particles of opposite charge, meaning one is positive and one is negative, opposites attract, and the way that we illustrate that with those field lines is that we show that this field goes all the way across. So we're passing through that space in between my two charges. Now notice that individually, we are pointing out of or away from this positive, and we are pointing in or towards this negative. You see here that these field lines kind of curl, and that's because we are showing that these lines, which would normally point straight out, are turning because they are attracted to that negative charge. And so that's why we end up getting that little curved shape on those field lines. As we look at our illustration over here on the right, here we have two charged particles that are the same, meaning that they are both positively charged. And so instead of showing these electric field lines to go out in all directions and including over here to the right, what we see is that these field lines are also curving, but instead of curving towards, like we had on the picture on the left, we can see that they are actually curving or curling so that they move away. So instead of coming straight out in this direction, this field line is actually turning because it is repelling from the positive charge on the right. And so as a result, what we end up seeing is right here, there is actually an area where there are no electric field lines. So I want you to understand that the field lines represent the area that these charges would have an effect on some other electrically charged particle. So if I were to place an electric charge right here, there's technically no electric field here, so that electrically charged particle would not experience any type of force because of either of these positive charges. The fact that those field lines have curled away means that in that particular space, there is no field coming from either of these charged particles, so there would be no interaction. I know that sounds crazy, but that's how that works, okay? So I need you to understand, let's just kind of review. Electric field lines. We are going to illustrate electric field lines with straight line vectors. There is a specific direction. We are going to point away from positively charged particles or objects, and we are going to point towards negatively charged particles or objects. We see that like charges repel. So right here, there is no field line, because in this space, that is the area where they have avoided each other, or they are moving away because like charges repel. Over here on the left-hand side, we see here in that same space, we have an electric field, which is showing us that here we do indeed have an interaction because these two are attracted, and so there is an electric field in this space because they are not avoiding or repelling, they are interacting between the two. All right, so let's talk about electric field strength. We should be able to calculate or give some sort of numerical value to represent how strong or weak the electric field is surrounding our electric charge. So we should already understand that the magnitude of our electric charge can affect how strong or weak the force is. So let's use that same thought process to help us give some sort of value to this electric field. So how great is this field surrounding my charges? Or if we just look at one individual charge, how strong is this field surrounding my electric charge? So what we need to understand here is that we can actually record some measured values if we take an electrically charged thing. Let's say that we know the value of an electrical charge, and we bring it so that it is forced to interact with our charged particle or our charge source, our source charge. Then we can observe, collect some data, and determine what that force was that the tiny little particle experienced. So what we say is that if we have some known charge, and so this is going to be the source of our electric field, right? And the electric field goes out in all directions here. And then we take some smaller little electric charge. So let's say that we have some positively charged particle here, and we're going to use this particle to test the field strength. So we're going to call this our test particle or our test charge, okay? This electrically charged thing is going to experience some force based off of the strength of that test charge. So the electric field in this case would be measured by the ratio between the strength of this little positive test charge and the magnitude of the force that it experiences. Now, that's what this equation is showing us. The font just kind of got a little off here, or the typing got off a little bit. So E equals F over Q is what that says. Now, this is going to be a force measured in newtons and an electric charge measured in coulombs. So you see that our unit for the electric field strength is going to be newtons per coulomb. Okay, so N divided by C. Now, what if we didn't have our little test charge to tell us what that electric field is? How else could we determine what that electric field is? Well, let's play around with the algebra for just a moment. We're supposed to know that Coulomb's law says the force experienced can be calculated knowing K, Coulomb's constant, the magnitude of our two charges, and the distance between them. So if we were to take this F for force and let's substitute it with what Coulomb's law means, so KQQ over R squared, and put that into our electric field formula, then we end up with this, okay? Now, let's make some sense out of what these Q's are real quick. There are two Q's because we have two electrically charged objects, particles, whatever our situation may be. So let's say that our source charge that we have here is going to be Q1. And let's say that our test charge that we originally had when we were observing the interaction of these two charged things is going to be charge 2. Okay, so if we look at the algebra over here on our newly written equation, we see that I have Q2 present twice in my formula. So if I look at the location of those Q's, I will see that I have Q2 in the numerator and I have Q2 in the denominator. And so those Q's end up canceling out. So if we do not have the luxury of using a small little test charge to see the force experienced in order to determine that electric field, we could simply calculate the strength of our electric field by using Coulomb's constant, this Q, which would represent the charge from our original source, divided by the radius. So the electric field strength can be determined based on the strength of the source charge and how far away do we want to place our object. Well, it makes sense that the field strength is going to vary by location. We already established that when we were just interpreting these field lines in the very beginning, okay? So the farther away we are, the farther away we are, then the weaker that electric field is going to be. The closer we are, so if we put a charge here where it is closer, then the greater the electric field is because we are at a smaller distance, okay? And so that's what this second equation is telling us. So we have two formulas that are going to allow us to determine the electric field strength. And I'm going to actually rewrite this for you because once again the font is a little off. So this would be E equals KQ over R squared. That 2 is an exponent. So these are your two equations for calculating electric field strength. Electric field strength is going to be represented in newtons per coulomb. And once again, the value for the constant K is 9 times 10 to the 9th. All right, so let's run through a couple of example problems just to make sure that you are comfortable with how all of this plugs in. So it says that Dominique pulls her wool sweater over her head, which charges her body as the sweater rubs against her cotton shirt. What is the electric field at a location where 1.6 times 10 to the negative 19 piece of lint experiences a force of 3.2 times 10 to the negative 9 newtons as it floats near Dominique? So our variables here are Q, which is 1.6 times 10 to the negative 19. Our force, which is 3.2 times 10 to the negative 9, and they are asking us for the electric field strength. So E equals F over Q. So E is 3.2 times 10 to the negative 9 over 1.6 times 10 to the negative 19. Now I'm just going to give you a friendly reminder here. I would really like for you to use that second and then whatever button has the little double E above it to represent your times 10. If you choose not to do that, then I'm going to remind you that you need to be putting this in parentheses so that your calculator comprehends that to be one value located in the numerator, and then this needs to go in a separate parenthesis so your calculator understands that to be one value located in the denominator. Otherwise, the calculator does not understand what you are asking it to calculate. All right, so this comes out to a perfect 2.0 times 10 to the 10th newtons per coulomb. Okay, let's look at one more example before we go. Here we have a fly, and it says the fly is going to accumulate 3 times 10 to the negative 10 coulombs of positive charge as it flies through the air. What is the magnitude of the electric field at a location 2 centimeters away from the fly? So for this question, our Q is a value of 3 times 10 to the negative 10, and it did say that was positive. Our distance between our source charge and this little positive charge is 2 centimeters. So don't forget that you have to go and convert that into meters for your math work. And they are asking us for the electric field strength. So for this question, we are going to use E equals KQ over R squared. So E equals 9 times 10 to the 9th. Times 3 times 10 to the negative 10. Again, please be smart with your calculator. Utilize those parentheses as needed. Divided by 0.02. Do not forget to convert. And then we're squaring our denominator. So this comes out to 6,750. So we would write our final answer